Ever feel like you need like a PhD just to keep up with all the latest AI stuff?
Yeah.
We're tackling that today. We're diving deep into this really cool paper about random forests.
Yeah.
No advanced degree needed, though. Don't worry about that.
It's one of those things I think that's really, really powerful, but the reasons why it works so well have been kind of a mystery.
Right.
Even for like seasoned data scientists,
Yeah.
this paper really shines a light on why they work well, and I think it's relevant for anybody in tech, especially folks that are using AI.
You had me at no PhD required.
Okay.
So we're digging into the paper is called Why Do Random Forests Work? Understanding Tree Ensembles as Self-Regulating Adaptive Smoothers.
Right.
That's a mouthful.
It is.
Before we even get into it, what's the quick takeaway for our busy tech listeners? Why should they care about this?
So this paper gives, I think, a fresh perspective on how random forests learn. Like, it's not just about combining a bunch of decision trees. It's really about how those trees interact to create this, like, smoothing effect. And this effect is kind of the key to understanding why random forests are so good at, handling all this crazy data we have and making good predictions.
Okay, I'm intrigued. Let's unpack this whole smoother thing.
Yeah.
What does that even mean in the context of AI?
So imagine, like, each tree in the forest is like an expert.
Okay.
Right? And they're each looking at the data, like a different part of it maybe, and they're making predictions. Some of them are going to be overzealous, right? So they're going to be like really latch on to certain data points
Right.
and make these really spiky predictions.
Okay.
But then when you average all those opinions out, you get something much smoother.
Okay.
Right.
So it's like a crowdsourced prediction where the outliers get balanced by the more reasonable voices.
Yeah, exactly. And the paper calls this the spiked smooth phenomenon.
I like it.
And it's really cool. They have these nice visual. If you look at figure 2 and 3,
Okay.
it shows you how, as you add more trees and as you add randomness, those predictions get way less jumpy.
So more trees, smoother predictions. Makes sense.
Yeah.
But why is that smoothness so important? What's the practical benefit?
So that smoothness is directly related to how well an algorithm can generalize to new data it's never seen before.
Right.
So instead of like memorizing the training data, it's actually learning some broader patterns, and that makes it more adaptable when you actually deploy it in a real-world scenario.
Ah, so it's not just about being right in the lab. It's about being right in the wild.
Yeah, exactly.
Yeah.
Exactly. And this is where I think it gets even more interesting.
Mhm.
So traditionally, we've thought about random forests being really good at reducing variance in the predictions,
Okay.
making them more consistent.
Right.
But this paper actually challenges that notion a little bit and says, well, they can also reduce bias too.
Okay, hold on. Before we go any further, can you give us a quick refresher on bias versus variance for those of us who haven't taken a deep dive into statistics lately?
Yeah, absolutely. So bias, you can kind of think of it as like you're systematically wrong. So you're consistently overestimating or underestimating something.
Right.
Whereas variance is more about being inconsistent. So even if the underlying pattern is stable, your predictions are kind of jumping all over the place.
Okay, got it. So low bias means you're hitting the target consistently, and low variance means you're not all over the map with your shots.
Yeah, exactly. Exactly.
But how do random forests tackle both of these at the same time?
So I think that's where, the insights of this paper are really valuable, especially for designing these systems
Right.
or implementing them. Because by combining all these different trees that all kind of have their own opinion, they can actually capture a wider range of relationships in the data,
Okay.
things that a single tree might miss.
So it's like having a team with diverse perspectives. They're less likely to get stuck in a single, potentially biased way of thinking.
Totally, totally. And in fact, if you look at figure 9, they have a really nice visual of that. And you can see how the forest can effectively cover this much wider range of predictions that no individual tree could.
This is blowing my mind. So it's not just about averaging out bad predictions. It's about expanding the types of predictions the model can even make,
Exactly.
making it more robust and insightful. But what happens when we throw real-world messy data at them? Data with noise.
Yeah, totally. I mean, and that's where I think the analysis gets really relevant to, everyday work.
Right.
They show how they perform under different levels of noise. And I think that's shown in figure 10.
Okay.
And it is pretty significant, the distinction between like in sample and out of sample.
Okay, before we dive into figure 10, Remind us again what those terms mean. In-sample versus out-of-sample predictions.
Oh, yeah, of course. So in-sample is just how well does the model do on the data it was trained on?
Right.
Out of sample is, okay, now I have some new data it's never seen before. How well does it do? Which is really the name of the game.
Right, because a model that just memorizes the training data isn't very useful in practice.
Mhm.
So what do they find about these in-sample and out-of-sample predictions with random forests? So back to those in-sample and out-of-sample predictions. What does Figure 10 tell us about how random forests handle noisy data?
Yeah, so figure 10 really highlights how this smoothing that we've been talking about really shines when it comes to noise.
Okay.
Especially like those in-sample predictions.
Yeah.
It's almost like the forest is saying, okay, I see all this chaos, but I'm going to find the signal. I'm not going to get distracted by all this like random noise.
Makes sense. It's like trying to have a conversation at a loud concert. You have to, like, filter out the background noise to focus on the signal, which is the person you're talking to. But what happens when the model encounters data it's never seen before? That out-of-sample data.
Right.
Does the smoothing still help even when there isn't much noise?
Yeah, and that's where I think it gets even more interesting. They found that even with really clean out-of-sample data, random forests still do really well.
Okay.
So that smoothing that helps you when there's noise also helps you generalize better, even when the data is like pristine.
That's wild.
Yeah.
So even when the data is pristine, this crowdsourced wisdom of the forest still outperforms individual decision trees. It's like the forest has a broader perspective, making it more adaptable to unfamiliar territory.
Yeah, for sure, for sure. And they took it a step further. They did some experiments where they specifically controlled how dissimilar the training data and the test data were.
Okay.
So they basically made the test data more and more foreign to the model.
So like throwing curveballs at the model, seeing how it handles data that's outside its comfort zone. I'm guessing this is where figures 11 and 12 come in.
Yeah, you got it, you got it. So figures 11 and 12 show this beautifully. They show how the forest actually adapts its smoothing level based on how different the data is. It's kind of wild, right? Like it can tell, okay, this data is really different from what I've seen before.
So it's like it has this internal gauge measuring the weirdness of the data and adjusting its approach on the fly.
Yeah.
Exactly.
Exactly.
That's incredible. But how does this like self-regulation actually play out in those figures?
So you can see as you make the data more and more dissimilar, the performance changes.
Right.
And what it does essentially is when the data is really dissimilar, it smooths things out more.
Right.
So it's being more cautious, right? Because it's like, I'm in this weird new area. I don't want to overreact to any one data point.
It's like the forest is saying, okay, I'm in unfamiliar territory, so I'm going to rely on the wisdom of the crowd and not jump to any conclusions.
Yeah.
This is a game changer.
Yeah.
It means you can potentially rely on these models to adapt to new data without constantly retraining or tweaking them.
Totally, totally. And I think that's, one of the things that makes this research really exciting, especially, again, thinking about applications. It's just, it highlights how this adaptability just makes them so robust.
Right.
And so valuable in the real world. And it kind of leads to, I think, an even bigger idea, which is, can we use this not just to make predictions, but to predict how reliable our predictions are?
So you're saying this research hints at an even bigger idea beyond just making predictions with random forests. What's this about predicting the reliability of our predictions? That sounds like next level AI.
Yeah, it's super exciting. And it really gets at this idea of, like, how do we build trust in these AI systems?
Right.
Especially if you think about our listeners who are, out there building real things.
Right.
It's like, what if instead of just giving us an answer, it also told us how sure it was?
That would be incredible. Like having an AI that not only makes a prediction, but also gives you a confidence score, telling you how much to trust it. That would be invaluable for decision making.
Totally. And so I think this paper kind of suggests that random forests could be like the key to this.
Okay.
Because if we understand how this smoothing changes based on the data, we might be able to actually quantify, well, how reliable is this prediction?
So instead of just getting a yes or no from the AI, you'd get, I'm 90% sure the answer is yes, or I'm only 50% sure, so proceed with caution. That would be revolutionary.
Yeah, exactly. Exactly. It changes how you interact with these things.
Right.
It lets you be more informed, especially if it's something where, you make the wrong decision, there are big consequences.
It's like the difference between having a GPS that just tells you where to go and one that also tells you about potential traffic jams or road closures.
Hmm.
That extra information allows you to make much smarter decisions.
Yeah, totally. Totally. And so, I don't know, I just think this is what makes this research so compelling. It's like it's really pushing the boundaries of what we thought was possible. It's moving beyond just prediction towards like really understanding uncertainty and reliability.
It feels like we've just scratched the surface of a vast and fascinating topic.
Hmm.
But for our listeners who need to stay ahead of the curve, what's the key takeaway from this deep dive into random forests?
I think the main thing is random forests, they're not just these black boxes. Like, we can actually understand the mechanisms that make them work, and they're really elegant. And so they learn, they adapt. And I think, like we talked about, potentially they can not only make predictions, but tell us how good those predictions are,
Right, yeah.
which is like super powerful if you're out there using these things.
It's a powerful reminder that staying up to date with the latest research in AI is essential for any tech professional. Even if you're not building these algorithms from scratch, understanding how they work gives you huge advantage.
For sure, for sure.
Well, on that note, I think we're about out of time, but to our listeners, definitely check out the full paper if you want to go deeper. And as always, thanks for joining us on the deep dive, where we make AI research accessible and hopefully a little bit fun.
Mhm.
We'll see you next time.
See you next time.